Have you ever just stopped and wondered how we get from a chunk of rock dug out of the ground to the gleaming metal that makes up our cars, our buildings, even our rockets? Well, today we're going to pull back the curtain on the incredible science of metallurgy.
I mean, seriously, think about that for a second. How on earth do you start with a pile of dirt and end up with something as massive and precise as a jumbo jet? It sounds almost like magic, but the answer is just some really clever chemistry that's all designed to solve one big problem.
You see, out in the wild, metals are hardly ever just hanging out in their pure, shiny form. They're social butterflies. They love to chemically bond with other elements, and their absolute favorite partner is oxygen. This locks them up in compounds we call ores. So the entire field of metallurgy really is a grand quest to figure out how to break that super strong chemical bond and set the pure metal free.
Okay, so our first strategy is all about using heat and, well, a bit of clever competition. You can think of it like a massive game of chemical tug-of-war. All these different elements are fighting over oxygen, and we're going to use the laws of thermodynamics to rig the game in our favor.
And this right here, this is our playbook. It's called an Ellingham Diagram. Now, I know it looks a little intimidating, but its job is actually super simple. Each line represents a metal oxide, and the diagram tells us exactly how stable it is at different temperatures. It's basically a power ranking for who holds on to oxygen the tightest.
So let's take a look. See how most of the lines slope upwards? That means as you crank up the heat, those metal oxides get less and less stable. They get weaker. But then, look at the line for carbon monoxide. It's the rebel here. It slopes down. It actually gets more stable the hotter it gets. And that little detail is incredibly important. Oh, and those sudden kinks in the lines? That's just where the metal hits a melting or boiling point.
And all of this leads to the golden rule of the Ellingham diagram. And it's wonderfully simple. If you want to break apart a metal oxide, all you have to do is introduce another element whose own oxide line is lower on the chart at that temperature. Being lower means it's more stable, so that element will literally just swoop in and steal the oxygen away. Lower on the diagram always wins.
Let's look at a classic matchup to see how this works. Check out the lines for aluminum and chromium. Aluminum's line is way down there, which tells us that aluminum oxide is insanely stable. And because its line is below chromium's, we know we can use aluminum powder to literally rip the oxygen right off of chromium oxide, leaving us with pure liquid chromium. It's that predictable.
And this right here explains why carbon is the absolute MVP of the industry. Remember that downward sloping line we talked about? Well, as you heat things up in a giant blast furnace, carbon's line just keeps diving down, crossing underneath the lines for tons of other metals, most famously iron. That makes it the perfect and super cheap tool for smelting iron ore into iron.
So this seems almost too easy, right? If carbon is this amazing at high temperatures, can we just use it for everything? Have we found the one-size-fits-all ultimate champion for getting any metal we want?
Well, the short answer is nope. Especially not for aluminum. The bond between aluminum and oxygen is one of the strongest in nature. If you look back at that diagram, carbon's line never dips below aluminum's line at any temperature that's even remotely practical. Our thermodynamic playbook just isn't going to work here.
So, what do you do when the chemistry just refuses to cooperate? Well, you stop trying to persuade it and you start forcing it. If you can't get the job done with heat, you bring in a different kind of power altogether, electricity.
This brings us to the electrochemical principle. And really, what we're doing is using raw electrical energy to bully a chemical reaction into happening when it really doesn't want to. Thermodynamics was about finding reactions that happen on their own. This is about giving a reaction a massive electrical push to make it go anyway.
The goal is actually pretty simple. If a reaction is naturally unfavorable, you can think of it like trying to push a boulder uphill. It's not going to happen. But by applying a big enough voltage, a big enough electrical push, we can force that boulder right up and over the hill. We're essentially making an impossible reaction possible through sheer force. And there is no better example of this principle in action than the famous Hall-Heroult process. This is how we get basically all the aluminum that's used in the world today.
Okay, so let's peek inside the factory. The whole thing happens in these huge steel tanks that are lined with carbon. That carbon lining is our negative electrode, the cathode. Then giant blocks of carbon are lowered in from the top. Those are the positive anodes. And the secret sauce is the electrolyte. The aluminum ore called alumina is dissolved in molten cryolite. This stuff is amazing because it lets us do the whole process at a much lower temperature.
All right, so you flip the giant switch, and here's what happens. First, the alumina breaks apart into positive aluminum ions and negative oxygen ions. Then, since opposites attract, those positive aluminum ions rush to the negative carbon lining of the cell. There, they pick up electrons and turn into pure liquid aluminum, which sinks to the bottom to be collected. At the same time, the negative oxygen ions are attracted to those positive carbon anodes hanging from the ceiling.
But here's the catch, and it's a big one. When the oxygen ions get to the anodes, they don't just bubble away. They viciously attack the carbon, literally burning the anodes away and creating carbon monoxide and carbon dioxide. This means that running an aluminum plant involves this constant, expensive cycle of making new carbon anodes and replacing the old ones as they get eaten up by the very process they make possible.
So there you have it. Two totally different but equally brilliant sets of tools that let us take plain old rocks and turn them into the very foundation of our modern world.
Let's put these two strategies head to head. The thermodynamic way uses heat and a reducing agent like carbon, and our guide is the Ellingham diagram. It's perfect for less reactive metals like iron. The electrochemical way uses pure electricity, and our guide is simply getting a positive voltage. This is the only way to go for the really tough, highly active metals like aluminum. Two different problems, two brilliant solutions.
From a simple chart that predicts chemistry to a colossal factory that forces it, the science of making metals is just an amazing story of human ingenuity. And it really makes you wonder, doesn't it? What other invisible chemistry is humming away all around us, quietly powering our world, just waiting to be understood?